I want to talk briefly about isomers. Now in Chem 222, we did a lot with isomers when we drew out all the isomers of butane or pentane or something like that. Isomers literally are everywhere. And isomers, when you start putting inorganic metals inside them, become even more interesting. So I want to kind of re-look at isomers here a little bit and get you ready for future classes where you may see some of this stuff happen. Isomers are important not just in organic chemistry, but inorganic as well. And you can have different kinds of isomers. So like you can have cis and trans, or you can have many different kinds of variations, as we're going to see here in a little bit. If you have an isomer, it means you have the same number of atoms, but they're put together in a different way. And you can't just rotate one version into the other, basically. And I want to just briefly talk about these different isomer types here because they're really interesting, and you might see them either in organic chemistry or maybe inorganic later on. A coordination sphere isomer is a type of an isomer that just is wild. It depends, it really differs here as to what atoms are complexed to the transition metal, i.e. which ones are being Lewis bases and which ones are just anions to the metal center cation. And this is just weird to think about even to me. Now, these examples right here, all right, we've got a cobalt center, 5 ammonias, a chlorine, and a bromine. But notice here in the first one, chlorine is on the inside of the brackets and bromine's on the outside. And in the second one, bromine is on the inside of the brackets, chlorine's on the outside. The ones on the outside are like regular anions. And so you place one of these in water, and the anion, whatever it is, will just float away in the water, basically. So in this one, you'd have bromide float away, but in this one, you'd have chloride float away. Now you can probably imagine that even though chloride and bromide have -1 charges and they're halogens, there will be times where they will react differently. If you react silver nitrate with these, the silver nitrate will attack whatever is outside of the complex ion. So when bromide is outside and you add silver nitrate, silver and bromide make very insoluble compounds. You'll end up with AgBr solid. But on the other example, chloride was on the outside. The silver will attack the chloride. You'll end up with silver chloride instead of silver bromide. So notice in these cases that the Lewis base on the inside connected to the cobalt is a bit stronger. It's resisting the silver nitrate, at least under these conditions. This is an example of a coordination sphere isomer. They're not super common, but they do pop up once in a while. Same formula, but if the anion is a Lewis base, or truly the anion, it can make a big difference. Linkage isomers, I still, to a point, just have a problem believing that they're real, but apparently they are. These two examples here are cobalt centers with 5 ammonias each, but the nitro is connecting to the metal center in different places. In the first one on the left, the yellow-colored solid, the nitro is connecting at the nitrogen, and the second one, the more red one, the nitro is connecting at the oxygen. They call the ones where the nitro is connecting at the oxygen the nitrito, and if it's a regular NO2 group, it's nitro. And you do have different kinds of reactivities, all right? In the second one there, the red-orange one, red color one, the nitrogen's running around. It could be a Lewis base to something. So you do see different kinds of reactivities. I kind of still don't always believe that these are real. It just seems like, oh yeah, your stuff just oxidized. You know, oxidation usually will turn the color of your complex a little different color. But there's been enough studies on it and stuff that it does seem to be real. My hat's off to these scientists. It does show a different kind of isomer than people usually see. Geometric isomers is really what we dealt with a little bit anyway back in Chem 222. And classic geometric isomers include things like cis and trans, all right, different combinations. And this also arguably would incorporate like isomers of pentane or something like that. But in this section, what I want to do is I want to talk more about cis and trans a little bit for inorganic complexes, and also talk about what's called Mare and Fact, and that's another kind of a isomer you'll see when it comes to metals. Like cis and trans in organic chemistry, cis and trans can lead to compounds with different colors, melting points, reactivities, polarities, all that kind of stuff. So it's pretty crazy and stuff then to think about all the possibilities that exist when it comes to chemistry. Here's the cis version, that's cis platinum. That's the one on the left. And there is a trans platinum kind of version on the right. And you can see that cis and trans in our inorganic chemistry comes down to 90-degree angles or 180-degree angles when you have a square planar complex. And that's kind of cool. The trans one would be less polar, definitely, than the cis polar. So it makes, or more, the cis one would be more polar and the trans would be less polar, definitely. So it can make a big difference. You can also have octahedral cis and trans. Octahedral cis means that the two atoms that are alike are 90 degrees, and octahedral trans means that the atoms are 180 degrees. So again, trans should be less polar, cis should be more polar. You can see some pretty drastic differences when it comes to these molecules. Mare and Fact are new players on the block, and Mare and Fact happen when you have three atoms that are the same around an octahedral center. So both these molecules listed here, there's a dark blue central atom, there's three light blue atoms, and three yellow atoms. If you look at the left one, the Mare version, which comes from Maradonyl apparently, two of the atoms, two sets of atoms, are 180 degrees the same. So if you look at this one right here, the top atom and the bottom atom, those are both blue, all right, and they don't change. And in the rotation part of the Maradonyl, you also have a yellow opposite, a yellow molecule right there. So Mare isomers are certainly less polar than the Fact, and Fact comes from facial apparently. All of the bond angles in a Fact isomer are 90 degrees. You don't have any 180 degrees blue metal blue bonds or yellow blue metal bonds. All of the angles in the facial isomer are 90 degrees. So because again there's differences in polarity, Mare and Fact can come in really handy. Fact is facial, and there is kind of like a triangle of atoms when you have a facial isomer that are all the same. There's like a blue triangle on kind of the top, and there's a yellow triangle, if you will, kind of opposite on the bottom. Maradonyl, though, has that 180 degree orientation, which makes it a little easier sometimes to see. The wildest kind of isomer, though, that we haven't talked about yet, but you'll probably talk about in organic chemistry if you take it, is when you get to what's called optical isomers. And these are wild. Now, before I start talking about this slide, I want you to look at your two hands, all right? You have a right hand and you have a left hand. And the right hand and the left hand both have a thumb, and they have a pinky, and they got the finger to flip somebody off if they cut you off on the freeway. No, seriously, you can use it for looking up dictionary entries, whatever. Okay, they're the same kind of fingers, but they're not the same, all right? Like, it's almost like if you put your right and your left hand together, they're like mirror images of each other, all right? But if you try to put the right hand in front of the left hand, well, that's not going to happen. Either it goes palm to palm, or the other sides are opposite and stuff like that. So your hands are example of what's called a chiral isomer. And if you have this handed type of isomer where it's like a mirror image, this leads to what's called enantiomers. So your hands are considered chiral because if you look in the mirror, it's like one is opposite the other. The right hand and the left hand would both be called enantiomers. And enantiomers are great about bending light. So they call them optical isomers because the light will actually bend a little bit from them. Substances can be chiral, have the handed nature, if they don't have a plane of symmetry. So for example, your hands don't really have a line that goes through them or anything like that. I want to talk about down here in these examples, isomer 1 and isomer 2, they all have a black central atom, and they have a white atom, a blue atom, a pink atom, and kind of a yellow atom around them, okay? So let's put isomer 2 2 and isomer 1 together. And let's pretend that we have a piece of glass or something like that. Notice how they kind of look like they're mirror images of each other, like blue to blue, yellow to yellow, whites on top, pinks in the back. They look like your hands when you put them next to each other. But isomer 1 and isomer 2, you can't rotate one into the other, all right? They're just like your hands. They look like they're mirror images of each other, but you can't rotate one into the other. So molecules with like carbon in the middle and 4 types of atoms around it, those are going to be chiral. You're going to have at least 2 enantiomers that can do different things. They'll bend light different. This is an area that kind of blew chemists' minds until about the 50s or so. In the 50s and 60s, they developed technology to identify different isomers if they were chiral. And that was no small feat. And for a long time, people really didn't understand what this was all about. Here's a picture showing, again, like your hands, all right? If you put your one hand, your left hand up to the mirror, it looks like the right hand is in the mirror opposite you. Or you can just put your 2 hands together, that's fine. This shows that you have a chiral system, and each hand would be considered an enantiomer. Enantiomers will bend light a little bit, and that's what makes them kind of interesting. Now, in the lower right is a cheesy example of a molecule that is also chiral looking at itself in the mirror, and you can see that they're kind of mirror images of each other. But if you were to physically take the molecules and put them together, you could align 2 of the atoms together, but the other 2 would be opposite. So you're not going to be able to superimpose one of those molecules on the other, just like you can't superimpose your hands on top of each other. These crazy optical isomers do some wild things. They possess a lot of identical properties. So for example, solubilities are similar, their melting point and boiling points are similar, usually their colors are the same, they will oftentimes have similar reactivity. But if you have an enantiomer and you react it with another chiral agent, you're going to see differences in reactivity. So the first way that they figured out that enantiomers exist is they use what's called plane polarized light. And plane polarized light is like light in just like one type of direction. And they will actually have different properties depending on if you have the one enantiomer or the other. Now, to get plane polarized light, you start with regular light, which comes out 360, all different degrees, and you use a polarizing filter, and that basically isolates the light along a plane, so an up and down plane in this example, but you don't have the left and the right or anything like that parts. It's not too hard, apparently, to make plane polarized light, and plane polarized light will sometimes be able to separate or figure out that you have enantiomers, and sometimes you can use that to figure out how to separate them. They use a lot of terms in enantiomers and chiral systems. They use what's called dextrorotatory and levoratory, and those get the symbols D and L. D means dextrorotatory, it means that the light is rotated to the right, and levoratory, which is left, means that light is rotated to the left. So if you have an enantiomer, only the left hand or only the right hand, you will see the light rotated to the left or the right. It's pretty cool. This is a way they can detect if you have enantiomers. But the problem with this is that a lot of times when you're making these, you'll end up with just as much left-handed stuff as right-handed stuff. They call those racemic mixtures. And your plane polarized light going through racemic mixtures, nothing's going to happen because you have just as much rotation to the left as you have to the right. It's really hard sometimes to tell that you have an enantiomer. You have to separate them out. If you want to separate out enantiomers from each other, i.e. get the left hands away from the right hands, you can use a chiral reagent. And a chiral reagent, i.e. only left or right hand, will sometimes be able to pull one enantiomer away from the other. Here's an example of this. Let's say that we have a racemic mixture of this cobalt compound. Now this cobalt actually has both D and L. This is a chiral system, and initially we have a racemic mixture, which means we have just as much left hand as right hand enantiomer, or just as much D as L. Now, you can take this chiral reagent, and these are not cheap, by the way, they're very difficult to make. This chiral reagent has the D form, and the D form of the chiral reagent only reacts with the D form in the racemic mixture. So down here, this is the cobalt complex again, but now it's got the it's got the D enantiomer, that D chiral reagent acting with it. The other one, the L version, just reacts with chloride and goes its own way. It doesn't do anything. So using a chiral reagent, sometimes you can pull the left and right hands one away from the other, which is not easy. Then you would have a pure enantiomer. You could put the plain polarized light through it and see it go left or right a little bit. It's pretty cool. This is a really interesting area of chemistry, and you have to be very detail oriented. Make sure you have the right enantiomer, stuff like that, the right reagent to react with. It can be very complicated, but the effects are also super important. The procedures that are used, again, are complex, but I can't emphasize enough how important it is. I want to talk very quickly about Ritalin and thalidomide. Now, thalidomide was a drug that was approved in certain European countries around the time of the 1950s, and it was supposed to help women when they give birth and stuff like that. It was supposed to be really good. Unfortunately, thalidomide was a product that had both a D and an L form. All right, there were two enantiomers, two hands in the form they sold to pregnant women. All right, well, the one form of thalidomide was wonderful and it did everything it was supposed to do, but the other form was really bad, and the children born had lots of birth defects and stuff like that. Really, really sad. There was a huge lawsuit that happened for many decades, as I understand, in England, and finally the victims got paid money for this and stuff, which is really crazy. It was never approved in the United States for use, but you will see sometimes old ads for thalidomide and stuff. Pretty crazy. Now, Ritalin is one you're hopefully aware of. It's used for kids that have attention deficit disorder. It supposedly makes them more mellow. Well, apparently Ritalin has a left and a right hand side enantiomer as well. It has a D and an L. And the one enantiomer is the good one. It helps the kids. But the other one apparently causes lots of problems and stuff. So be aware that these kind of things are very important when it comes to pharmaceuticals. If you don't have the right enantiomer, you could have really bad reactions. And finally, I couldn't help but resist and put up Samuel L. Jackson, which is his real name, and also Samuel D. Jackson, because D and L are the two enantiomers, and you can see they're looking the opposite way. Oh, my sense of humor.